Good morning. I have already completed how a wave travels through a medium. That was the first part. And that too in three-dimensional equations we wrote. Then after that, we talked about normal incidence. Okay, reflection, transmission, reflection coefficient, transmission coefficients, all this we have done. Now what we'll do is we'll look at reflection at an oblique angle. What is the meaning? The meaning is if I have a medium 1 and a medium 2, here what happens is you draw the, my God, what bad figure. Okay, so here I have my interface between medium 1 and 2. Let this be the normal A n cap. Now, if a wave comes and hits at an angle not normal, if it hits at an angle not normal, you have something called theta I, which is the angle of incidence. Then you will see that part of the wave will get transmitted, making an angle called theta t. It's a transmission angle. Part of the wave will get reflected. This is going to be theta r. Okay, so I think we already discussed this part, right? Reflection at an oblique angle, did we? Yeah, we have discussed. I'm sorry. We have already discussed this. We wrote the equation for Maxwell's equations also. Then we talked about the angle of incidence. We talked about the angle of reflection. Then we saw how the frequency doesn't change when there is a transmission or reflection. Then we wrote k vector in various x component, y component, z component. Then under root of the square of these things, when you add up, you get your k vector. Then we saw that because of the boundary conditions, there are two laws that are obeyed. One is the law of reflection, that is theta I equal to theta r. Then after that, we talked about Snell's law. Snell's law says that theta I by theta r will be equal to the refractive index of the second medium divided by the refractive index of the first medium. Or if you're talking in terms of velocity, the velocity of the first medium, velocity in the first medium divided by velocity in the second medium. And here we are making an assumption that k is equal to beta because the two mediums involved are lossless. Ben, is that right? These are the things we have talked.
Yes, ma'am.
Yeah, and after this we solved one problem. See, look at that one class. If I lose, you see, we are completely. So one thing is we did one problem on this. Then after that one problem I recorded and then gave it to you people. Now what we will do is the same thing. We will continue. We will continue and talk about polarization. We will bring in polarization into the picture. So the first thing we are going to see is parallel polarization. And what is polarization? Polarization by definition is the direction of the electric field. In the electromagnetic field, the direction of the electric field is given the status of the that will stand for the polarization definition. So we talk about two types of polarization here. We will be talking of two types of polarization. One is called parallel polarization and the other will be called perpendicular polarization. One is called parallel polarization, the other is perpendicular polarization. Okay, now before that, I have already defined something called the plane of incidence. Previously also I talked about plane of incidence. Okay, let's see what is plane of incidence. Let us say that this is z equal to 0 and z greater than 0 is medium 2 and z less than 0 is medium 1. Okay, now if a wave is, and let us say that I'm going to fix my xyz coordinate system. So let's say that this is, so therefore this becomes my z axis. And if I say that my y axis, okay, if I say that this is going to be my x axis, if I say that this is my x axis, this is my y axis, then what will be my z axis according to the right hand rule? X cross y. That means out of the plane of this figure is going to be my y axis. Is that right, guys? Is that right? Okay, now what we'll do is let us take a wave or let us take a ray of a wave and let us say that it is, this is my an vector, that is a normal at that point, and let us say that this is the way my ray is coming and hitting. Okay, now you have to consider, so what is this direction? This is the direction of the k vector. This is the direction of the k vector. K vector is the direction in which the wave is propagating. and then the normal at this point is given as AN. And you can clearly see that both these vectors, AK vector and your AN vector, that is the direction of propagation and the normal, are lying on one plane. They are lying on one plane. Which is that plane? Anyone? Anyone? I'll rub some of this.
XZ.
Huh?
XZ.
Yes. The wave, it is lying on the XZ plane. It is lying on the XZ plane. The entire thing is happening on the XZ plane. And we have seen in the last class that according to the laws of reflection and the Snell's law, the reflected angle, the incident ray, the reflected ray, and the transmitted ray, they will all fall on one plane. And what is that plane called? That plane is going to be called the plane of incidence. That plane is called the plane of incidence. Okay, the angle made, the plane containing the incident ray and your normal. So that's going to be called the plane of incidence. Now, in comparison with this, look at your electric field. Look at your electric field. Your electric field has to be normal to K vector. That's what we have been seeing. AE and AH have to be normal to AK vector. They have to be normal to the AK vector. So now what we'll do is we'll draw our electric field. Our electric field, let us draw and say that this is my electric field. If I say that this is my electric field, look at this. I have this, okay? I have my plane, this is my AK vector. Now I have my electric field. Electric field is certainly perpendicular to AK vector, but it can be like this, it can be like this, it can even be lying on this particular XZ plane. Are you finding that? Are you able to understand what I'm saying? In my figure that I have drawn here, can you see that my AE vector, electric field vector, is perpendicular to K vector, but it is falling on the plane of incidence. Any doubts on this? Ramya?
No, ma'am.
Okay. So if it is falling on that plane,
ma'am, it's not falling on the plane, no, ma'am. It's
what?
just on the Z equal to Z less than 0 plane only it is lying, no, ma'am.
No, what is your plane? What is your plane? The plane is Z less than Z equal to 0 is this plane, Okay. Your ray is coming like this. Your ray is coming like this. Your normal is this. So the plane containing these two is your plane of incidence. So that is your XZ plane. X is equal to 0 is this plane. Or
okay,
X
so
less than 0 is this plane.
Huh? Entire X is equal to 0, X greater than 0, X less than 0 is the plane of incidence, ma'am.
No, no. Good you asked that question. I will again draw and explain. You have to understand this. If you understand this, it becomes very easy. I'll just draw this again. So I draw a plane. This is not a line, remember, it is a plane. Okay, and this is a plane parallel to x-axis, and it is lying at, I'm sorry, it is a plane parallel to the z-axis. It is perpendicular to, this is my z-axis. It is perpendicular to the z-axis and lying on z equal to 0. Is this point clear?
Yes, ma'am.
Okay. Now, whatever is on this side, all those things are z greater than 0. Whatever is lying on this side, they are all z less than 0. So I'm calling this as medium 1, I'm calling this as medium 2. Clear?
Yes,
see, one of you keep it unmute. Okay. Next, what I will do is, let me draw the other axis. So let me draw my axis here. Okay. So I'm defining this as my x-axis. And this becomes my z-axis. This is my origin. Okay. And now I have to also, are you able to see why is it saying it's not responding? Guys, you're able to see?
Yes, ma'am.
Yeah. So this becomes, I'll put a dot here to show my y-axis. Clear? X, Y, Z I have defined.
Yes, ma'am.
Okay.
Yes,
now what I will do is, let me just draw a normal. A normal, I'll call this as AN. Okay. Now at this point, a wave is incident and it is hitting. This is also clear? What is the direction of this?
Yes,
What is the direction? This is AK cap. Okay. This angle will be angle of incidence. Okay. Now what you do is, for this ray, which is whose AK is like this, imagine an electric field. The electric field vector will definitely be perpendicular to AK vector. It will be definitely perpendicular to AK vector. Okay. So this is my AK vector. I can draw my electric field perpendicular to AK vector, but it can be anywhere on this. It can be anywhere. It can be like this. It can be like this. It can be like this. Are you getting that point?
Yes, ma'am.
Okay. Now, if AE vector is lying, on this plane, which is this plane, the plane that we are having is the plane that we have here is called the plane of incidence. And which is that plane here? It is lying on X and your Z plane. It is lying on the X and Z plane. So XZ plane is plane of incidence in my example. Okay. And if my AE vector, which is perpendicular to AK vector, is lying on this plane, then it is called parallel polarization. Are you getting that, guys? So it is lying, that AE vector is lying on that plane of incidence. Therefore, we call it as parallel polarization. If on the other hand, this is the plane of incidence. If on the other hand, AE vector is like this means what? It is along the y-axis. Are you getting that? If it is along the y-axis, either plus or minus, but along the y-axis, if my A vector is there, that means AE vector, the electric field is perpendicular to the plane of incidence, and that is called perpendicular polarization. This concept, if you understand, everything is clear.
Yes,
did you understand this?
Yes, ma'am.
Okay, now let us go ahead.
AK is in the XZ plane, no, ma'am?
Yeah, AK is lying on the XZ plane.
If it is perpendicular, then it will be in the XY plane, electric field.
No, it can be perpendicular to, so just draw. How do I do that? I can actually draw one. Just think of this. This is my, okay, how do I show? This is a plane. This is a plane, but my hand is a plane of incidence. Okay, my hand is my plane of incidence. I am drawing my electric field. The electric field can be like this. That means it is along the y-axis. But the electric field can lie on this also and still be perpendicular to K vector. Yes or no? You take a paper.
It's hard to imagine.
You take one paper. Imagine the paper to be angle of the plane of incidence. Okay. This you can do. And that plane is your XZ plane.
Plane is
XZ plane. Right? Take a paper. That plane is your XZ plane. Your K vector is lying on that.
Ma'am, it is XY plane, no, ma'am?
Which one?
Plane of incidence.
Plane of incidence. See, I have defined what are my X, Y, Z. This is my Y axis. This is my Y. Y equal to 0 I'm sorry, this is my Z axis.
Z equal to 0 will be XY.
Z equal to 0 is a plane, man. Z equal to 0 is a plane. A plane containing a plane perpendicular to the Z axis. Z equal to 0 is a plane perpendicular to the Z axis. Okay, that is clear?
Yes, ma'am.
Now what we are doing is, we are talking about the other axis. What are the other axes we are having? X axis and Y axis. Y axis will be in which direction? It will be out of the plane of the paper.
Out of the plane, yeah.
Out of the plane. Okay, now you are going to draw a normal on the Z plane. Okay, we call that as AN. Now, what is this plane? What is this plane? Which axis? What will be this plane? Plane of the paper.
XZ.
It will be XZ.
And plane of the plane, it is like to Z axis, we are making a plane perpendicular.
You see the plane of this screen. What is the plane of the screen?
Screen, it is XZ.
XZ, okay. And on that plane, you are drawing your AN vector and you are drawing your K vector.
Okay.
Are you understanding? They are all lying on a plane.
Yeah, understood.
Now, to this you imagine a perpendicular. The perpendicular can be along the y-axis. perpendicular to the plane, or it can be perpendicular to k vector and it can be lying on the same plane.
Ma'am, I think you can proceed now. I'll just have a look later on.
Okay,
Classes
so
getting
no,
okay.
that's not difficult to understand. Okay, the plane of incidence is XZ plane, and if your E vector is lying on that plane, it is called parallel polarization. If it is perpendicular or if it is along the y-axis, then it is called perpendicular polarization. Okay, now let's just go ahead. Okay, so here is a picture of the incident wave, the reflected wave, and the refracted wave. You look at this. So I will now call Ki vector. This is my Ki incident. This is Kr for reflected and Kt for transmitted. Clearly, they are all going to be different because they are in different directions. K is actually showing the direction also. So you can see because the direction is changing, all of them will be different. Ki, Kr, and Kt. We have to use different things to denote them. Next thing is angle of incidence, angle of reflection, angle of transmission. Okay, now what I will do is I have to write an equation for, in the phasor form, I have to write an equation for the electric field. For the electric field of the incident, I have to write an equation. So what I will do is, I'm considering parallel polarization. So my EI vector is lying on the plane. It is lying on this plane. Which is this plane? This plane is the XZ plane. It is lying on the XZ plane. Okay. So I will translate this, and I have just put here, I just drawn one diagram here to show my EI at Z equal to 0. Okay, and let me call it as EI naught. Let me call it as EI naught. And you can see that this vector will make an angle theta I with the boundary. See your mathematics, theta I will make, EI will make an angle theta I with the boundary. Is this convincing? K is going to make an angle theta I with Z axis. Perpendicular to Z axis is your X axis. So if you draw a perpendicular to K vector, this vector also will make an angle theta I. Clear? My God. Ki makes angle theta I with normal, with Z axis. Okay, now draw a normal to Z axis. Normal to Z axis is X axis. Okay, similarly draw a normal to your K vector, that is your EI vector. Therefore, both these will also make an angle theta I. Are you following the argument? What to do now? Hey, nothing, man. Don't get scared. I want at least one of you to tell if you have understood.
Ma'am, it's hard to imagine, ma'am.
Look, this theta I, this is clear to you?
Yes, ma'am.
Right. You are understanding that this is a normal?
Yes, ma'am.
This is a normal to the K vector. Okay. K vector is making an angle theta I with this normal.
Yes.
Right. Now what you do is take the perpendicular to the Z axis. Take a perpendicular to the Z axis. Z axis is here. Perpendicular to Z axis will be X axis. Is that fine?
Yes, ma'am. Yes.
Right. Now take a perpendicular to K vector. If you take a perpendicular to K vector, it is going to be EI.
Yes, ma'am.
Right. So now what I will do is, for your sake, I will just translate that fellow here. If I translate that fellow here, he is going to be called EIO. What will this angle be?
Theta
This angle will be theta I.
Okay.
Understood now?
Yes, ma'am.
Yeah. So this and all, I'm wasting time because you fellows cannot imagine. Okay. So now this is what I have tried drawing here. I know it's difficult. That's why I drew and came. So it is here. Okay. So now find the components of these two. What will be the components? This is my Z axis and this is going to be my X axis. So you can see that the components will be in this direction and in this direction. Yes or no? Okay, so therefore
Yes,
the
ma'am.
components will be ei naught cos theta I along the ax cap direction, and similarly this will be minus ei naught sine theta I in this direction. Minus because it is going towards z equal to z negative, and this point is z, this plane is z equal to 0. Clear now?
Yes, ma'am.
Yeah, that is the reason. What you will now do is you will write your ei naught. Normally you will write yes, you will write it as the magnitude, and then you will write the rest of it. So here you see you'll be writing ei naught cos theta I ax minus sin theta I az. Clear to you? Okay, and similarly, last class itself we saw that if you take your ki vector, this is my ki vector also I can resolve in the same way. If I resolve in the same way, my ki vector I have shown last time, and this angle is going to be theta I. Therefore, my ki vector will have a component beta 1 cos theta I, and this side it will be beta 1 sine theta 1. Okay, is this point clear? Because I am able
Yes,
to
ma'am.
write these two, I will be writing them here. So beta 1 sine theta I, beta 1 cos theta I. Okay, and this x and z are there because you know kxx plus kzz, that is the general form of the equation. Yes or no? General form of the equation would be cos of kxx plus kzz, right? So for this kx, I am writing beta 1 sine theta I. Similarly for kz, I am writing beta 1 cos theta I. Clear? Okay, now this is what we are going to do for the magnetic field and the electric field, for the incident ray, for the transmitted ray, and for the reflected. But did you understand this one, at least one equation did you understand? Nothing, don't get
Yes, ma'am.
scared. You are simply on the xz plane. For ki, you have written the components. Similarly, for ei naught also, you wrote the components. You are writing everything in terms of components, x component and your z component. Simple. Okay? Don't get scared. You just look at it, you'll understand. And you will not have to remember all this. I'm only trying to show you how we arrived at this. Otherwise, you will wonder what is all this. So I just written it. Okay. By the same logic, you are writing your H also. Now let us go to the next page. In the next page, you are similarly writing the equation for reflection part of the electric field and the magnetic field. But beta 1 is what you will be writing there also. Only thing is the angles will be theta r, theta r. Okay, and you can just draw the components and see wherever minus is coming, why minus is coming. You will know if you draw the perpendicular at those points. Similarly, come to transmission. Transmission also will look exactly like incident. Only thing is here beta 2 will be there and theta t will be there. Clear to you? Okay. Now that we have written all this. So equation 11a, 11b, 12a, 12b, 13a, 13b. They are simply the electric fields of the incident, transmitted and reflected, and the magnetic fields. You are writing. That's all. Okay. Now what you do is apply the boundary condition. Now apply the boundary conditions for electric field and magnetic field. The boundary condition is that the tangential component should be continuous. Okay. So now using another thing that you have already done is theta I equal to theta r. This you got in the last class. Okay. Now what you do is add 11a and 12a. Add 11a and 12a. What is 11a? 11a is the equation for the electric field. It's the equation for the electric field. Take 11a, add it to 12a. Okay. If you add it to 12a, 12a is the reflected. So that means you are taking the electric field for the incident and the reflected, okay, and you are going to add them. When you add them and apply the boundary condition that theta I equal to theta r at z equal to 0, then what you get is going to be a simple equation ei naught plus er naught cos theta I equal to et naught cos theta t. Okay. Now, similarly, you can do for the magnetic field also. When you do for the magnetic field, you will get 1 by eta 1 into E I naught minus E R naught equal to 1 by eta 2 E T naught. Eta 2 comes because the transmitted is in the second medium. Eta 1 is in the first medium. Both the incident and the reflected are in the first medium. Okay, that's all. Next, what you do is we call these two equations as 14A and 14B. By now, you should be able to guess what we are going to do. What we are now going to do is we are now going to write the equation for the reflection coefficient and the transmission coefficient. What is reflection coefficient? Reflection coefficient is ERO by EIO that we have seen in the last class. Electric field reflected divided by the incident at Z equal to 0. And we will add a subscript parallel here because we are talking of parallel polarization. So look at the equation we are going to get. Eta 2 cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. Does this equation remind you of something? Or you can also write ER not equal to tau parallel EI naught, where this tau is called the reflection coefficient. Now what I want you to do is just recall what you have studied for normal incidents. There you wrote tau equal to eta 2 minus eta 1 divided by eta 2 plus eta 1. Similarly, transmission coefficient T, we wrote it as 2 eta 2 divided by eta 2 plus eta 1. Now what I want you to do is just if theta I equal to theta R. What is the meaning of saying theta I equal to theta R? If theta I equal to theta R means if it is normal incidence that you have already seen. So into these equations, if you put theta E equal to theta, into this if you put theta I equal to theta R equal to 0 equal to theta T. Okay, so that is your normal incidence. Put that and see what will happen. Each of these costs will become 1. When all these cost terms become 1, you will be left with what is the expression that you got for normal incidence. Please, you will follow these classes only if you study every day. Otherwise, Greek and Latin. Okay, so you got the expression for tau parallel, you got the expression for T parallel. Now, both these equations are called Fresnel's equation for parallel polarization. That means for perpendicular polarization, other equations are going to come. So look at this. I have asked you to set theta I equal to theta T equal to 0. If you do that, equation 15A and 16 will reduce simply to your known equation for normal incidence. And the way to remember this also, I will tell you the shortcut to remember this. Eta 2 means you are already in the second medium. So cos theta t, transmission angle. Eta 1 is you are talking about the relationship between incident and transmitted. Therefore, here you will have theta I because you are in the first medium. Similarly, come to this. Here, because you are in the, okay, here there is a difference. Eta 2 cos theta I will come, okay, and eta 2 cos theta 2, and these two will be the normal thing. Okay. Okay, so now if all this is there, now let us go to, I just want to check eta, this T parallel, I just want to once check from the book. Okay, one of you just check and let me know later whether I have made a mistake here. We'll just check that. Okay, next. Next, since theta I and theta t are related, Snell's law said that theta I by theta t is equal to u1 by u2. Now what we will do is cos of theta t, we'll write it as under root of 1 minus sine square theta t, that is your trigonometry. And instead of sine square theta t, we will make a substitution from here. Because after all, from here you are getting sine theta t equal to u2 by u1 into sine theta I. So just use this. Okay. So you have eliminated theta t in this way. Okay. Now what you do is, if you substitute this in the equation for reflection parallel and transmission parallel, you will arrive at this relationship between tau and t. Relationship between tau and t. Once more, what you do is, if you put theta I equal to theta t, you will be left with 1 plus T equal to 1 plus tau equal to T. This was the equation that you got for normal. Okay, these are the checks whether you are writing it correctly. Okay, next thing, you look at this. When the reflection coefficient is 0, what is the meaning of saying reflection coefficient is 0? Reflection coefficient is 0 means when the reflection coefficient is 0 means the entire ray is getting transmitted. There is no reflection. Please understand, I'm going to teach a concept here. When the reflection coefficient is 0, when the reflection coefficient is 0, that means no reflection is happening. No reflection is happening. Let me just try to draw a figure here. I have my plane, I have my normal. Okay, now I am going to show you a ray that is coming. It is hitting at some theta I, but no reflection is happening. All the wave is simply getting transmitted. The entire wave is getting transmitted only at some angle theta t. Okay, this is theta I. This angle is theta. This angle is theta I, and this is the incident ray. Okay, but no reflection is happening. No reflection is happening means tau parallel is, gamma parallel is 0. Okay, now when will this happen? When will this happen? This will happen whenever theta I is equal to an angle called Brewster angle. Have you heard of Brewster angle?
No, ma'am.
No, okay. So it's a new thing. There is an angle called in optics. If you are going to take a paper called fiber optics, there is one paper in the next semester. One elective is there now. Dr. Leela is handling. Okay. So if you take that elective, all these concepts will come there. So there is an angle called Brewster angle. There is a particular angle called Brewster angle, and because it is parallel polarization, we are putting this parallel symbol also. So at that angle, what will happen is no reflection will happen. All the wave will simply get transmitted. Now this angle is called the polarization angle. This is the principle behind a polarizer. This is the principle behind your polarizing glass and all that. That means conveniently some part of the light will get transmitted and there will be no reflection for that particular light. Okay, this is the principle of a polarizer, and this particular angle is called the polarizing angle. And there is another name, it's also called the Brewster angle. It's called the Brewster angle or the polarizing angle. So look at this picture. So there is an incident angle at which the reflection becomes 0 and there is no reflection. This is called the Brewster angle. It's also called the polarizing angle because this is very important. Listen, it is also called a polarizing angle because an unpolarized incident wave, so here I have shown you a picture. This picture is not from your book. I've shown you a picture. Okay, so this is my boundary. This is my boundary. Let us say z equal to 0. An unpolarized wave is hitting. Why am I calling it unpolarized? You look here, it is having both a perpendicular component and a parallel component. It is having a perpendicular component and a parallel component. A component of electric field lying on the plane of incidence, and there is a component which is perpendicular. So that means it is unpolarized. Both components are there. So when you allow this to hit at a Brewster angle, okay, when you are going to allow it to hit at the Brewster angle is given here as theta d. When it is hitting at the Brewster angle, what happens is no reflection should happen. No reflection should happen for the parallel polarization. Parallel is these arrows. These arrows means the parallel polarization component. So that parallel polarization does not get reflected. So what is getting reflected is perpendicular polarization. What is getting reflected is perpendicular polarization, and some part of perpendicular also continues to get transmitted. So what will be essentially transmitted will be this parallel, okay? Parallel will get transmitted completely. Some part of perpendicular also will get transmitted, but what is reflected will not have any parallel. Reflected will not have any parallel. It will be completely a polarized light. So if you want to separate out parallel, you have to have successive polarizer layers. So it will get refined each time it is getting transmitted, it will get refined, and finally you will get completely polarized parallel. Okay, and reflected will be completely polarized perpendicular. Did you understand this, guys?
Yes, ma'am.
Yeah, so this is the job of the polarizer, and this will happen only at the Brewster angle. So this is called the Brewster effect. So the Brewster effect is utilized in a laser tube. In a laser tube, you make a laser, and in a laser tube, what happens is you will use quartz windows. Okay, and the quartz window will be set at the Brewster angle, so that the light which comes from the laser source is going to hit it at the Brewster angle, and what comes out is going to be purely polarized. The emitted ray will be the transmitted ray. So the transmitted ray will be a polarized light. Did you understand this? Okay,
Yes,
so this
ma'am.
is how the polarizer works. And then next thing is, oh my God, lot of theory. So now you had this equation for the reflected parallel. Okay, now into this, you set theta I equal to theta B Brewster angle. At that time, the reflection will be 0. And if reflection is 0, now look at this. What does this meaning? Reflection is 0 simply means the numerator is 0. Numerator is 0 means eta 2 cos theta t equal to eta 1 cos theta b, right? Now what you do is, instead of cos theta t, you put 1 minus sine square theta t. Similarly, instead of cos theta b, you put 1 minus sine square theta b. Okay, and now go for a lossless medium. For a lossless medium, you know that eta equal to under root of mu by epsilon. So assuming that both of them are lossless, here you will write, instead of eta 2 square, you will get mu 2 by epsilon 2. Similarly, here you will write mu 1 by epsilon 1. Okay. Next, what you will do is you use Snell's law. You have to use and set, instead of theta I that you have already done, you will write theta b and write your Snell's law. If you write your Snell's law now, what you will get is sine theta t equal to under root of mu 1 epsilon by mu 2 epsilon 2 sine theta b. Nothing new here, guys. Nothing new here. Sometime back you wrote sine theta I by sine theta r equal to velocity in the first medium by velocity in the second medium. What is the equation for velocity? It is c into under root of mu 1 epsilon 1 divided by c into under root of mu 2 epsilon 2. C and c will cancel out. So you're getting this. Okay, only thing is, instead of theta I, you will write theta equal to theta B parallel. So you are writing Snell's law at the polarizing angle. Okay, next what you do is, you get rid of sine square theta t. You get rid of sine square theta t in this equation. Okay, so then what happens, you will get mu 2 by epsilon 2. How do you get rid of sine theta t? Using this, get rid of sine theta t in this equation. When you get rid of sine theta to t, you will get a pure equation in terms of Brewster angle. So you can guess what I'm trying to do. Finally, I'm writing an expression for the Brewster angle. I'm writing an expression for the Brewster angle. Expression for Brewster angle will look quite compact. Next, what we'll do is, if this, already we have said both the mediums are lossless. Now, additionally, we are going to put a condition. If it is lossless and at the same time, non-magnetic. If both the mediums are lossless and at the same time non-magnetic. Non-magnetic implies mu1 equal to mu2 equal to mu0. It's like free space. As far as magnetism is concerned, it is like behaving like free space. It is not going to have any magnetism. So then look at this equation. In this equation 21, if you get rid of mu, you will end up with this beautiful equation 22. Okay, and you can still make it simpler. You can write it in terms of tan When you write it in terms of time, it just becomes this. Okay. And what is this equation 23 trying to tell you? Equation 23 is trying to tell you that for any combination of epsilon 2 and epsilon 1, what is epsilon 1 and epsilon 2? They are properties of the medium. Okay. For any combination of two mediums, there has to be a Brewster angle. There has to be a Brewster angle. So with this, we are concluding the theory of parallel polarization. You do one thing. I'm going to, my syllabus is getting slowed down now. Okay. But I don't want to go ahead unless you have digested today's class. Can you do this and come in the next class? I have put in box those things that you are supposed to remember. Whatever is put in box, you have to remember. Only thing is just understand the logic, just understand, draw on a paper the figure itself, understand what is parallel polarization and what is perpendicular polarization. Okay, then go to these equations that I have set up and then put the conditions and see, like theta I equal to theta R, put the condition of Snell's law, then put the condition for polarization and see whether I am correct. That's all. Is that clear, guys?
Yes, ma'am.
Sri Chakra, కళ్ళు తిరుగుతుందా?
లేదు.
లేదా? లేదు అంటే you were not listening to the class.
I was listening, ma'am, but I have to get back through again.
What about Ben?
Ma'am, I have to look through the video again.
You have to look at the video. That means nobody is listening.
Listening, ma'am, but these equations somehow relating it to different things and remembering is difficult.
Sahiti.
Small, minute variations here and there.
Okay, what about Sahiti?
Oh, ma'am, I have to go through it
Please
again.
tell your other classmates also if they are going to go on like this. I am going to go final exam also. It's going to be a 2 or 3 hour exam. It is going to be a pakka on paper exam only. Because I am not compromising anywhere with the teaching. So why should I not do? And already I have shown you how we can efficiently conduct an examination. Only thing is there were small hitches. Next time you will upload the paper. And how many of you have checked your paper? Have you all seen your paper, the corrected paper?
Yes, ma'am.
Does it look like our normal correction?
Yes, ma'am.
What more can I do? I'm thoroughly disappointed by some students not attending class. I have already reported them. And what I will do is I have the attendance for every class I'm taking. Lastly, because all those quizzes were conducted for checking your presence in the class and how you are doing, the 20 marks I will remove and give 0 for all those students who don't have attendance. Tell them. We have been allowed to do that. We have been allowed to do that. Attendance is not compulsory. It doesn't mean that you don't come to the class at all. That is very bad. And these are difficult things. Even if you come to the class, you cannot follow. And fellows are sitting there, not even bothered to see the recording ones. And if they are all thinking that they are going to copy, they're terribly mistaken, because my histogram is already showing 2 peaks like this, one here and one here. Nothing in between. All of them are going to end up with D grade, and all my recordings are there. Nobody in the management can point a finger at me. Every record, every word I utter to you, I am recording here. Tell those idiots. This is very bad, very, very unprofessional what they are doing. I'm going to have only this kind of exactly like what I do in a class is what I'm doing here. And I am also conducting my exams in the same way. Next time a sound was disturbing you, next time I'll ensure that I will use the TV in my house and I will do it. I'll put you all on my TV. You are only, after all, 65 people. All of you can be accommodated on a big screen. I'll put you there and I will mute everybody and you will write your examination. This time some fellows did not put the video on. Next time you don't put on your video, I'll give 0 marks for such fellows. This time I didn't give 0 because anyway they got 0.5 mark only, all those guys. So I know that they didn't gain anything, so I gave them marks. Is that clear, guys? Snigdha? Snigdha? Left the system on and went off, I think.
No, ma'am, I'm here.
Okay.
I just can't unmute it. Sorry.
You can't unmute. Okay. So what do you say? Are you able to understand what is happening in the class?
Yes, ma'am, but we need to refer it once.
Yes, you have to. I know it is a tough syllabus. And I'm supposed to have done this and one more problem in this class. That is the way the syllabus has to go. But I know you are all mathematically weak. I don't know what to do. Like this, you should be able to see it, no? You're not able to imagine a plane. You're not able to imagine a perpendicular. You have to do that.
Ma'am, that came because of the one class we missed, I think.
Huh?
That one gap we got last class.
So what?
So little mix up here and there.
A little mix up. I myself, I forgot what I had taught. What I taught. But then since I prepared for the till the last class, my preparation is there. So I can teach any portion anytime. No problem. Okay, so we should actually have done one problem. So next class I'll do 2 problems. I have to do fast 2 problems. Please come prepared. Okay, and perpendicular polarization, I will go fast because parallel polarization you see and come, perpendicular polarization I have to go fast. The equations will all be different. Equations will be different that you can guess, because if I'm talking about as a exact plane, then my polarization is going to be perpendicular, means it's along the y-axis. So all equations will be different. Okay, so please see and come and tell your friends that they are going to miserably get a D grade or an E grade only. There will be no B and C. That's my guess, because the average for the last test was 5 marks. Is that fine? Please tell them. I'm confident about what I'm doing. Yeah.
Test 1 or the quiz, ma'am?
Test 1 average out of 20 is 5.
Oh, okay.
Okay. Fellows who came to the class, most of them have done well. Most people who came to the class have done well. Okay. Good day then.